right, so here's the video I was promising to make since I am in COVID quarantine. Gotta love these things. All right, so anyways, as we started talking about last time, we started talking about the air resistance or the retarded forces or drag forces. So let's start talking a little bit more about those. So as we mentioned, this is a highly complicated equation which depends on the velocity which that we're actually moving at. So in most cases, this is very complicated. As we mentioned in class, basically that means is that we have to experimentally determine what this thing is actually doing. But as long as we have sufficiently slow enough speeds, then we can most of the time make some sort of approximations to be able to actually solve it. But sometimes those approximations actually fail, because again, as I mentioned in class, sometimes we have things raised to odd powers, so like 3/5 powers, etc. But again, what we do know is that when an object is actually moving in some sort of fluid, so again, here's my object, this thing has some sort of velocity, let's say my velocity vector v, and let's say there's some other external forces acting against this guy, external. Then we know is that this thing is going to feel a drag force, where that drag force typically will be in the opposite direction than as the velocity vector. So in most general cases, what will happen then is that our F drag, or our retarding force, will then be equal to a negative of this guy's magnitude. So this is the magnitude then of our drag force here. Times then v hat, right? Where v hat is just the vector, which then is the same thing as the vector divided by the magnitude. So it's just a unit vector defining the direction then of the velocity. So this is my v hat in this case. So all this means then is that what? As the trajectory of this object starts to change, of course, then the direction of the drag force will change. So if my trajectory looks something more like this, then at any stage around here, the velocity, of course, is tangential to the direction of the trajectory, which means then that the drag force is in the opposite direction as that. Now, again, as long as our velocity is slow enough, then what that means then is most of the time, at least for a good number of problems, what we can typically do then is actually do a Taylor series expansion of this magnitude of our drag force. So what that means then is that we're going to rewrite our drag force then via f of v as then being equal to some Taylor series expansion. The sum over I of then vi, which is then in our case going to be the same thing then as v1 v plus then v2 v squared plus then higher order terms. Now, in most cases, if I'm talking about something like air, again, at sufficiently slow speeds, typically these are going to be the two dominant terms, which we're usually just going to write then as the linear drag force plus then our quadratic drag force. So linear just means that in this case, the drag force is then directly proportional to the velocity which is moving, and then the quadratic is then going to be proportional to the velocity squared, which is said moving. Now, these terms arise again depending on the velocity at which it's moving at. So typically the first term here, the linear term, arises basically due to viscosity. And this guy is usually going to be directly proportional then to the medium and the linear size, or the viscosity of the medium and the linear size of the object itself. So proportional to the viscosity of the medium and linear size of that. Now, the quadratic one, which is actually the one that we looked at when we talked about in 205, a long time ago, but basically the quadratic one comes about mostly from the fact that it has to try to accelerate the air or the fluid that's in front of it out of the way. So this comes from the fact that it needs to accelerate. fluid out of the way. So this one typically is proportional then to the density of the medium. This is proportional to the density of the medium. And the cross-section area. So now typically what ends up happening though is in most cases, again, as long as we can do this Taylor series expansion, which again, we can't always do this Taylor series expansion, but let's assume that we actually can. What ends up happening then is that one of these two terms will be dominant over the other term, which basically just means that in most realistic cases, if it's moving slow enough, then it's going to be dominated then by the linear velocity. But if it's moving fast enough, then it'll be dominated by the quadratic. Now, again, this is more so in air. If I'm talking about something more about, say, like liquid, so something like a water, so an incompressible fluid. In that case, then typically almost never will you find the linear case. It's almost always going to be the quadratic case. But again, if I'm talking about something which is moving in air, most of the time what ends up happening then is that what? My motion will be dominated by one of these two scenarios. So either if it's moving slow enough, it'll be dominated by the linear term, but if it's moving fast enough, then it'll be dominated by the quadratic term. So basically it just means that we ignore one in terms of the other one, which is going to simplify our expression, which is going to make our life so much easier in most of these cases. So let's talk about how this is going to work kind of in a, again, a more realistic type situation. Okay, let's see, here's my object, which has my mass of m. And again, let's just say this thing has our external forces, which are acting on it. External. Again, let's say it's moving temporarily in this direction. So my velocity vector. So this is my velocity hat vector. And then this is going to be my drag. So let's look at how this is going to work out in terms of Newton's second law in two different scenarios. So first, let's look at the linear case. So in this case, let's say that, again, the quadratic portion of the drag force can be ignored. So this is going to be much, much smaller than the linear term, so we're going to ignore it. So in this case, then my F drag will then be equal to minus F linear and times the velocity vector. Good. So if I wrote this out, then this is going to be equal to minus d1 times the velocity in the v hat direction. Good. So let's look at Newton's second law. What happens in Newton's second law in this case then? So in this case, we know that Newton's second law says then that the sum of the forces, which in this case is going to be our F external force, then minus our d1 v hat, or sorry, the vector, then must be equal to the mass times the acceleration, which is r vector double dot. Now, remembering that v, though, is equal to r dot, then I can rewrite this then as my f external minus then d1, the vector, then is equal to m times v vector dot. Now, as long as I'm working in Cartesian coordinates, which is one of the nice things about Cartesian coordinates, is that, as we've seen in class, we talked about before, this becomes separable, which basically means then all we have to do then is look at the forces which are acting in each individual direction, and then solve our differential equation in each different direction. So, for example, in the x direction, we're then going to have what? Mx double dot, right? Which is the same thing then as m v sub x dot, then must be equal to the x component of the external forces, then minus b1 vector component vx. All right, so this is going to be what's true in the x direction. And then in the y direction, we're going to get something very similar. We're going to get md dot y is then equal to the y component of the external forces, then minus b1 vy. Now, of course, here I'm assuming that the external forces are constant. So these guys are constant, at least in terms of velocity. Excuse me. So, but they don't have to be. They can be time dependent and other things as well. But in this case, I'm just kind of assuming that they're constant. But the thing to note about here is that these guys are completely separable, which basically means that what's happening in the x direction as far as the velocity is concerned only depends on what's happening in the x direction. What's happening in the y direction only depends on what's happening in the y direction. So again, this is just saying that the instantaneous acceleration in the x direction depends on the instantaneous velocity in the x direction, as well as the forces in the x direction, while the instantaneous acceleration in the y direction only depends on the instantaneous velocity in the y direction. So it's completely uncoupled. So I don't have anything in the x depending on what's happening in y and vice versa, which is very nice. Right? Now, let's look at the other case. So now if I have the quadratic case, which again means that the linear is going to be much, much less than that of the quadratic. So it is subdominant, so we can ignore it. What happens in that case then is that our drag force then is going to become equal to minus the quadratic drag times velocity vector v hat, which is going to be the same thing then as minus v2 times v squared in the v hat direction. Okay? Now, this guy I can rewrite in terms of v vector like I did previously by again noting that what v times v hat is the same thing as v vector. Right? So that means this thing, I can pull out one of the v's. So this guy's going to be the same thing then as minus v2 times v times v times v hat. But then grouping these two guys together, that's the same thing as v vector. So finally, this is going to become minus v2v, which is the magnitude of the velocity times v vector. Okay. So in this case, Newton's second law then is going to become what? M times v dot is then equal to, again, my external forces, but now minus v2, the magnitude or the speed times then v vector. So hopefully you can kind of see that this is actually already starting to not look very nice in the fact that now we have a v magnitude in there, which means that now when I work in Cartesian coordinates again, what happens is now if I look at the x component, so my x component then is going to become what? mvx dot is then equal to, again, the x component of the net force or the external forces, which is very nice. But now in the second term, there's some complication because now I'm dealing with the magnitude of the velocity, which means that it's going to be the square root of vx squared plus vy squared times then vx. And then in the y direction, we get an mdy dot is then equal to f external in the y direction minus then v2 times, again, the square roots of vx squared plus vy squared vy. So the presence of that magnitude of the velocity causes problems in the fact that now these two equations are fully coupled. So these are now coupled equations. So what does that mean? So basically what that means then is that, again, notice that here, the instantaneous acceleration in the x direction depends on the instantaneous velocity in the x direction. It's good, but it also depends on the instantaneous velocity in the y direction. So it depends on what's happening in the y. So whatever's happening in the x direction depends both on what's happening in the x and in the y direction. And then same thing here. So the instantaneous velocity, or sorry, instantaneous acceleration in the y depends on the instantaneous velocity in the y here and here, but it also depends on the instantaneous velocity in the x, which again means that these guys are fully coupled with each other. So this kind of complicates things, especially if something is moving in 2 dimensions, which I can choose only 2-dimensional motion because most of the time I'm not going to have any tangential forces which are going to cause this guy to move perpendicularly, unless I'm considering a rotating coordinate system. We'll talk about that later. So in this case, then I can always rotate my 3-dimensional problem into a 2-dimensional problem by the fact that I can choose whatever coordinate system I want to. So here, again, my 2-dimensional problem in general is going to be very difficult to solve. And most of the cases, or most of the time anyways, we're going to have to solve this guy numerically to actually see what's going on because of the coupling between the two different systems. But so good. So this is then going to be our two equations of motion that we're basically going to look at. So again, in the linear case, we're going to use this guy. We're going to have to solve these in Cartesian coordinates, knowing what the external forces are. And then in the quadratic case, we're going to have to use this to then solve for our dynamics of our problem. So basically, all we want to start doing now is start looking at some concrete examples and seeing how we actually do this in practice. So our first example we're going to look at is a nice simplified problem, which we're going to look at simply horizontal motion. So this is going to be our first example. So basically, we're going to look at this and look at it for different velocity ranges. So meaning we're going to look at it for linear resistance as well as quadratic resistance. So good. So let's say I have some object. My object then is moving horizontally where it has some velocity v. So here's my velocity v. So in this case, then a drag force would be off in this direction. So it's going to be drag in the opposite direction of the motion, which again means that my velocity units vector will point in this direction. Now, since it's moving in horizontal motion, so in this case, we know there's actually a normal force and a gravitational force, but since it's only moving along, say, a horizontal track, those two forces will be equal and opposite, so they cancel, which means in this case, my external forces are simply equal to 0. So in this case, then, let me go ahead and arbitrarily call this my x direction. Then I can say that's what m v dot then is going to be equal to minus v1 times v. So this becomes my differential equation that I have to solve. Now, before we move on to this, look at the solutions for this, let's build our expectations like we have done previously in class, just to kind of see what should actually happen based off our physical principles. So what should we actually expect? So what we should expect is what? Since the drag force is in the opposite direction as velocity, this thing has to slow down. Right? So what we know then is that the velocity will then decrease over time. Right? So velocity decreases as t increases. So this is one thing we should expect. Now, this retarding force, which is actually acting on it, notice that since it depends on the velocity, what's going to happen then is what? This is going to get smaller, or at least the retarding force will get smaller on it as the velocity gets smaller, which means that, again, our acceleration will also be time dependent. So in this case, our acceleration will be time dependent acceleration, again, causing this thing to go to 0 until it eventually stops. Now, since this thing slows down and stops, we should expect then that it should go over only some sort of finite range. So again, if I give it some initial velocity, let's call that guy d0, this thing is only going to eventually stop at some stage. So this thing is going to go some sort of finite distance of x. Now, furthermore, again, since the velocity is getting smaller as time goes on, then the drag force is getting smaller, it's going to turn out, and we'll see that in a little bit, but we'll try to argue that now, is that our velocity should be exponentially decreasing. So this thing's going to go something like e to the minus d. So these are our expectations. So again, this thing has to slow down. Our acceleration has to be time dependent. This thing is going to go only a finite distance, and our velocity should be somehow exponentially decreasing. Now, mathematically, of course, you can think of that as the fact that I have a dv on one side and a v on the other side, so I'm going to get a natural log. So this thing has to become exponential. But anyways, so let's start off in here and let's actually solve this thing. So again, what we want to do then is use our separation of variables. So again, I have an m dv dt is equal to minus v1 times v. I want to get anything that's v on one side and anything that's not a v on the other side, so meaning all the t's and everything else. So here I'm going to get a dv divided by a v is equal to a minus v1 over m times t. Now we're going to integrate both sides. I'm going to integrate this from the initial velocity v to the final velocity. And I'm going to integrate, sorry, it should be dt. Integrate this side. from 0 to t, using that b1 and m are constant. So again, the b1 term, this is a term that's going to depend on things like viscosity, the linear size of the object, and etc. But you'll derive that in your homework. So left-hand side, of course, is the natural log. So I'm going to get the natural log of v divided by v0 is then equal to minus v1 over m times t. Again, since we want v, we're going to exponentiate both sides. So I get v then is equal to v naught e to the minus b1 over m times t. So indeed, what we find then is our velocity is time dependent, and it is actually exponential. And for this guy, I can define a time constant. So define a time constant of m over b1. So this guy can be rewritten as v e to the minus t divided by tau. Tau is our time constant. So what does the time constant do? So we talked about this in both tool 6 primarily, but in tool 5. But what the time constant tells you then is how quickly is the velocity decreasing. So in this case, you can think about the fact is when the time is equal to the time constant. In this case, then my velocity has decreased by e to the minus 1. Okay. So basically, my velocity decreases by an exponential amount per each individual time constant. Now, notice that in this case, of course, my velocity doesn't go to 0 until t goes off to infinity. So basically, this thing is going to take an infinite amount of time for this thing to stop. So as it's slowing down, it gets slower and slower and slower and slower, but it has enough velocity to keep slowly going that it takes an infinite amount of time for this thing to actually stop. Now, the next thing we want to look at is our last prediction was that this thing is going to go over some sort of finite range. So now what we want to do is take this expression here and then determine what is the position as a function of time. So let's go ahead and do that. So let's start off with that expression. So I have v, which we know is dx dt is equal to v initial e to the minus t divided by tau. This form. Again, using my separation of variables, I'm going to bring anything that's an x to one side, anything that's not an x to the other side, which means I'm simply going to multiply both sides by dt and integrate. So our left-hand side is going to be dx integrated from x initial to x final, is then equal to v0 integral 0 to t, and then e to the minus t divided by tau. Left-hand side, of course, becomes x minus x initial, is then equal to v0. Integral of that guy is just the derivative divided by, so I get a minus, 1 over tau. There we go. And then, in this case, I'm going to get e to the minus t divided by tau, evaluated from 0 to t. Plugging all that in, so I can bring in the minus sign to change the order of my bounds. So let's go ahead and do that. So it's going to become a t to 0. So finally, I'm going to get a v0 tau times then 1 minus e to the minus t divided by tau. Now, so what do we know then? So we know then, again, is that what? This thing doesn't stop until t goes to infinity. So let's look at how far it actually went in that time frame. So as t goes to infinity, what happens then is that x becomes x0 plus then v0 times tau. We're using the fact again that tau is simply m over b1. This guy then becomes what? x0 plus b0 m over b1. So this is then the distance at which it travels. Pardon me. So in this case, we can see that everything here is actually finite. So x0 is just whatever the initial position was, which I can always call 0. v0 is just whatever the initial velocity was, which is finite. M and v0 both finite. So indeed, again, this thing travels a finite distance. Great. So good. So again, going back to our expectations, all this stuff matches our expectations. We said the velocity should decrease as a function of time. It does. It decreases exponentially. It does. Since velocity changes over time, that means we have a time-dependent acceleration, basically because this guy is exponential. And we said it should go only a finite range, which indeed does. Cool. Now, something else we could have done is instead of solving for the time, we could have directly found the position as a function of velocity or velocity as a function of position. So just for funsies, let's go ahead and do that because sometimes that's going to be convenient. And again, to remember how we did that, going way back to what we did in chapter 2, we said that dv dt, we can use the fact that what? V is a function of both x and t because x is also a function of t. And then use our chain rule. So we rewrote this as dv dx times dx dt, but dx dt is the same thing as the velocity. So it's going to be v times dv dx. Oh, good. So let's plug all that. So from here, we can then rewrite our differential equation as, so again, we had an m ddt, or dv dt, which is going to be the same thing as v dv dx, is then equal to minus b1 v. Okay. So good. So from here, nicely, the v's here cancel, so that's good. So all I'm going to do then is what? Integrate the left-hand side, divide both sides by m, and multiply both sides by dx. So I get a dv integrated from v initial to v final, then is equal to minus b1 divided by m times then what? The integral from x initial to x final of then dx. So I get a v minus v initial is then equal to, we pull out the negative sign, so I get a b1 over m times then x initial minus x final. So same thing as before. Basically, all we just see is exactly the same expression. So if I use this solver back when b final is equal to 0, I still get then that's what? Yeah, that's fine. X final then is equal to x initial plus then b1 over m. I'm sorry, b0 m over b1, which is the same exact expression. So again, here I don't have to worry about the fact that the time has to go to infinity for this thing to stop. I mean, it's nice to know, but for the most part, that's pretty much irrelevant. All that matters is the fact that when this thing stops, when v goes to 0, again, it travels some sort of finite distance. So nice, that's kind of nice and easy. So now let's look at the quadratic case. Let's look at the quadratic. A little more complicated. Not too bad. Good. So the quadratic case, we're then going to have that what? md dot is then equal to minus b2 times b squared. So again, let's think about our expectations before we move on. So our expectations, again, number one, we should say that this thing, again, should slow down as time increases. Which again means that the acceleration should be, again, time dependent. And then number three, so this one is a little bit harder to say. So again, we know that this thing is going to eventually come to stop, which means it's going to go over some sort of distance. So in this case, we want to know, is this going to be a finite distance or an infinite distance? So at this stage, it's very hard to tell until we actually determine. Now, the other thing we can look at is we can also ask the question, so does the decrease more rapidly than e to the negative t divided by 10? So is it going to decrease more or less rapidly than this guy? Now, the reason we can ask that is because now notice that the right-hand side, when the velocity gets small, it gets, the retarding force then gets even smaller, right? Because now it's going as a velocity squared. Now, initially when this thing is moving, of course, the retarding force is going to be very large because it goes as the velocity squared. But now, since it's going very slowly, the velocity squared then can become even smaller, which means the retarding force is going to be very, very small. So there's kind of this two different things going on. So for high speeds, it's going to slow down very quickly, but then for low speeds, it's going to slow down very slowly. So basically, we want to see overall what should happen. But again, our expectations, the two things we can say for certain are these two things. So it is going to slow down. It is going to stop at some stage. And the acceleration, of course, will be time dependent. But now it's hard to say these two things. So is this guy going to be greater or less than, so meaning more rapidly or less rapidly than the previous linear case? And then is it going to go a finite distance or is it going to go a infinite distance? So let's find out. So cool. So let's start looking at this. So in this case, again, let's divide both sides by m. So I get a dv dt is then equal to minus b2 divided by m times then b squared. Now again, b2 here is going to depend on things like the density and the cross-sectional area and all that good stuff of the object in the fluid, or the density of the fluid, I should say. But again, let's not worry too much about that. You'll derive that in homework again. So from here, separation of variables, I'm going to divide both sides by v squared, multiply both sides by dt. I'm going to get a dv over v squared integrated from the initial velocity to the final velocity, then is equal to minus b2 over m integral then of dt integrated from 0 to t. So left-hand side, what does my left-hand side become? So the integral of 1 over v squared is the same thing as negative 1 over v. I'm going to evaluate that then from the initial velocity to the final velocity. And then that's going to be then equal to minus v2 over m times t. From here, I can use this side to cancel out this side. So get rid of that negative sign. So I'm going to get a 1 over v minus 1 over v initial, then is equal to v2 over m times t. So let's solve this then for v. So what I finally get then is that the velocity is equal to the initial velocity divided by 1 plus v2 v0 t over m, which I'm going to define that then to be v0 over 1 plus k times t, where k then is going to be equal to v2 v0 over m. So this is just a new constant that I'm defining. Oh God. So what's going on? So in this case, we can see then as t goes off to infinity, right? Because again, this thing is going to only stop. So the final velocity will go to 0 only when the denominator goes to infinity. Because the numerator in this case is a finite constant. So I can't make that guy 0. So I have to make the denominator infinity to make the overall thing 0. So what that means then is when this thing starts going to t is equal to infinity, my velocity then is going to be directly proportional to 1 over k times t. Now, if I plotted these two things, meaning if I plotted my quadratic velocity, right, or just say the velocity as a function of time. So in a quadratic case, this thing is doing what? 1 over t. 1 over t quadratic. And then the exponential case is doing something like this, right? This is the linear case. So this is e to the negative t, which is the linear case. So indeed, what actually ends up happening then is that my velocity in the quadratic case actually decreases faster because a 1 over t is much faster than that of the quadratic case. So let's compare the solution of the linear case then to the quadratic case to get a feeling for the differences between the two cases, comparing the two velocities. Let's look at those. So let's look at our two velocities. So let's look at my v linear divided by my v quadratic. So they both have v zeros in them, so they're going to cancel out. So basically what I'm left with then is I get a 1 plus k times t times e to the minus t divided by tau. So what happens in this case? So let's first look at early times. So let's look at early time. So basically, I'm just going to say that t is much, much less than 1. Okay, so I can do a Taylor series expansion on this guy. So in this case, I get v linear divided by v quadratic is then approximately going to be equal to 1 plus k times t times then the Taylor series expansion then of the exponential, which is the same thing then as what? 1 minus t divided by tau plus some higher order terms. Order terms that go as t squared. So let's look at this. So this is going to be the same thing then as what? 1 plus k times t minus t divided by tau, and then plus higher order term that goes t squared. This is going to be the same thing then as 1 plus k minus 1 over tau all times t. All right. So what does this mean? So what this means then is that at early times, right, so for small times, this approximation here says that these two things are about the same. Right, so as long as t is small, I can ignore the second term and all higher order terms, which means then that's what the relationship then, or the proportionality between the linear velocity and quadratic velocity is basically 1, which means that initially they are decreasing at about the same rates. Okay? But again, as t goes off to infinity, what happens then is that's what? The exponential will cause this thing to go to 0, which means then that v linear divided by v quadratic goes to 0, which basically means then that v quadratic is going to be much, much bigger than v linear. So then for large times, the quadratic velocity then will be larger than that of the linear term. Now, let's answer the second part of the question. How far is this guy going to go? So let's look at how far this guy. So again, let's start off with the fact that the velocity is equal to dx over dt, which is then equal to, again, v0 divided by 1 plus k times t. Again, in this case, I'm going to multiply both sides by dt and then integrate. So I get the integral, again, of dx from x initial to x final is then equal to v0 integral 1 plus kt dt from 0 to t. Left-hand side, of course, is just x minus x initial, and that's going to be equal to 0 times. So in this case, let's use a u substitution. So here I'm going to say u then is equal to 1 plus kt, which means du then is going to be equal to k dt. So in this case, I can replace dt with du over k. So there's my k integral du over u, and now my bounds. So when t is equal to 0, then that tells me u then is equal to simply 1. And then when t is equal to t, that goes to 1 plus k times t. So good. So this then is going to become equal to v0 over k natural log of u evaluated from 1 to 1 plus kt. Or finally, I get a v0 over k natural log of 1 plus kt divided by 1. Which, of course, is the same thing as simply v0k natural log of 1 plus kt. Now, notice the interesting thing about this one is that as t goes to infinity, which again, we already said back here that this thing won't stop until t goes to infinity, this thing has no limiting case, which basically means that if I plotted the position as a function of time, so this is my position as a function of time, this thing's going to do something like this, right? Which basically means that as time goes off to infinity, the distance at which this thing is traveling is also going to go to infinity. So as t goes off to infinity, x also goes to infinity. So basically, what this thing means is, unlike the previous case, the other one went a finite distance, where this one actually is going to trickle all the way out to infinity. Now, this may seem weird, but it actually kind of makes sense if we think about it. So again, for early times, for large velocities, said is that what? This thing is going to slow down at a fast rate. Right? But as the velocity gets smaller and smaller and smaller and smaller and smaller, the size of the drag force gets smaller and smaller and smaller and smaller and smaller, until the fact that it eventually will be moving so slowly that the drag force will be so small on it that it'll approximately just basically be equal to zero. Which means that the amount of time it's going to take for this thing to actually fully go to zero velocity is going to be very, very long. Which basically means that this thing is going to be moving so slowly, but it's still going to be moving that it's eventually going to trickle all the way out to spatial infinity. So in the second case, this one's going to go all the way out then to spatial infinity. Good. So last thing we're going to do is, again, use our trick of rewriting the velocity in terms of the position by, again, using the fact that we can use the chain rule. So my left-hand side, again, is going to become m dv dx is then equal to negative v2 over m times v squared. So this v here will cancel off with one of those v's. So we get a dv dx is equal to minus v2 over m times v. Again, we use our separation of variables. dv over v integral from v initial to v final is equal to minus v2 over m integral initial position to final position dx. So I get a v minus v initial, then, oops, sorry. I get a natural log, sorry. I get a natural log of v over v initial is equal to minus v2 over m x minus x initial. There we go, that makes more sense. Again, to get rid of the natural log to get the velocity, I got to exponentiate both sides. I got v then is equal to v initial e to the minus v2 over m x minus x initial. So here, this is another nice way to see that this thing is actually going to go all the way out to spatial infinity. And the reason for that, again, is that's what, mathematically anyways, by the time this thing goes to zero, this thing has to go to infinity to make sure the exponential goes to zero, which means in that case, x has to go to infinity as my velocity here that goes to zero. So indeed, my velocity is exponentially decaying as a function of the position. But again, as we made sure we said before, physically what's really going on is that as this thing is getting slower, the retarding force on this thing is now super small because it now goes as the velocity squared. So as the retarding force gets smaller and smaller and smaller, the velocity is going to go to zero much slower, which means that it's going to keep moving forward at a very slow velocity, but the retarding force is going to keep it basically rolling in the fact that it's not big enough to really cause it to decrease its size too quickly. So this thing is going to just trickle all the way out to spatial infinity, where we'll finally come to rest at spatial infinity. So that's our first example. So next time we'll start looking at vertical motion. So we'll say we have one-dimensional vertical motion where we're just going to have gravitational force near the surface of the earth, so just the weights m times g, and then look at both, again, the linear or the quadratic drag forces that are acting on it. We'll learn some new stuff, so we'll do some mathematical techniques, so things like integrating factors and all that kind of stuff, Taylor series expansions, all that, all the good things. So yeah, so we'll leave it off on here, and then yeah, we'll pick up with this on Wednesday.